Hi, this is a video about chemical kinetics. In the Brown and LeMay textbook, it's chapter 14, and specifically we're going to try to learn how to write a rate law. All right, so here we have a balanced equation, and it's a decomposition reaction of nitrogen dioxide. And as time goes by, what happens is the reactants concentrations go down, so they decrease. And you start making your products. So the nitrogen monoxide and the oxygen concentrations go up. Now, to write a rate law, you only worry about the reactants. You don't worry what's about on the product side. And rate is equal to K, which we're going to talk about later, but it is a rate constant. And then it's times the concentration of your reactants raised to some order. And now this reaction order does not come from the balanced equation. And today's video is going to teach us how to determine this reaction order. So rate laws, it's just an expression that's going to tell you how does our rate depend on the concentration of the reactants. And so here again is our rate law for the reaction that we saw for the decomposition of nitrogen dioxide. K is our rate constant. We are going to be spending some time also making sure that you're careful with those units. N is called the reaction order. And for us just starting out, it's either going to be 0, first, or second order. And this K and the reaction order, they are determined experimentally. You don't get any information from the balanced equation for this. All right, so these are the important points so far. The products don't appear in the rate law, so don't even worry about them. That reaction order, again, determined experimentally. It has nothing to do with the balanced equation. So how do we determine it experimentally? Well, first of all, what we're doing is called a differential rate law, or people might just call it a rate law. And it is going to show how the reactants depend on the how the reaction depends on the reactant concentration. So we're using this method of initial rates. And what you're going to see is you're going to see these rates for several different experiments that were determined almost immediately after the reaction started. So right after you started the reaction. And you're going to see different experiments with different initial concentration of your reactants. And then you're going to see how changing those reactant concentration affects the rate. And then we're going to be able to figure out the reaction order. So I thought we would just go ahead and look at this equation here. We would like to figure out the rate law for this equation. And we have 3 different experiments. We've got experiment 1, 2, and 3. And in these experiments, see in our first experiment, the ammonium concentration was 0.1, the nitrite concentration was 0.005, and then that was that initial rate. But in experiment 2, well, we kept the ammonium the same. We doubled the NO2, the nitrite concentration, and look what happened. Our rate changed. Now notice, between these reactions, only the nitrite changed, and then we saw its effect on the concentration. We kept the ammonium the same, and we doubled the concentration of the nitrite, and it indeed did have an effect on the rate. It made the rate go twice as fast. Then look at experiments 3 and 2. Here, we kept the nitrite concentration the same to determine the effect that the ammonium has on the rate. When we doubled the concentration of the ammonium, it also changed the rate, and it looks like it also doubled the rate. All right, so how do we use this information? Well, first of all, let's write our generic rate law. So rate is equal to K times our concentration of all of our reactants, ammonium, the ion, raised to some order, and our nitrite raised to some order. And our job is to figure out the orders, and this is the language, the order with respect to ammonium, that's X, and the order with respect to nitrite. All right, well, let's go back and look at that data again. Let's look at experiments 2 and 1. So we're going to compare experiment 2 to experiment 1 to determine the effect of nitrite's concentration on the rate. Now, we have to be keeping everything else constant in order to see the effect of nitrite. And we're just going to go ahead and write rate laws for experiment 2, plugging in these numbers and comparing it to experiment 1, and we should be able to get a reaction order out of it. Okay, so we are comparing reaction 2 to reaction 1. And I kind of like to put the faster reaction on the top, and then that way I am not dealing with fractions. So rate 1 over rate 2. Okay, so here we go. So rate 2 was 2.7 times 10 to the negative 7th. Rate 1 was 1.35 times 10 to the negative 7th. And now remember, the top is from reaction 2. And in reaction 2, the ammonium concentration is 0.1 molar raised to the x, and the nitrite concentration is 0.01 raised to the y. And then all over, this is from, these numbers come from reaction 1, which is 0.100 to the x and 0.005 to the y. Now this reduces down to 2. The k's are the same, so they're going to cancel. Oh my goodness, this all cancels. And 0.01 divided by 0.005 is 2 to the y. So therefore y must be 1. So the order with respect to nitrite is first order. So we figured out one of the orders already. So this is first order. All right, now what experiments will we use to figure out the order of ammonium? Where does ammonium's concentration change and where does nitrite stay the same? Well, that's experiments 3 and 2. And so I would like to put experiment 3 on top, experiment 2 on the bottom, and we're going to do exactly the same thing. So let's go ahead and do this. Let's see if I can remember these numbers. Or let's see, 3 is 5.4 to 2.7. Okay. All right, so rate 3 over rate 2. Oh, I forgot it already. 5.4 to 2.7. Okay. 5.4 times 10 to the negative 7th over 2.7 times 10 to the negative 7th is equal to K, the concentration of ammonium to the X, and the concentration of the nitrite to first power. We figured out that's a 1 now. Over K, ammonium's concentration, and the nitrite concentration, which is here. Oh, rats, I forgot these numbers. So plug in those numbers, whatever they are. These numbers are going to be the same because the concentrations are the same. This turns out to be a 2. Our K's cancel. And again, when you plug in the concentration here and here from experiment 3 and 2, you're going to get 2 to the X, and X is also 1. All right, so what we have is our rate law now. K is equal to the ammonium ion's concentration times the nitrite ion concentration. We figured out the orders. Now, again, we used 2 different experiments where one concentration remained constant to see what effect the other concentration had on the rate. And so the overall reaction order for this is just adding these 2 numbers together. So this is probably the easiest thing we do all year. N is 1 plus 1, 2. So it's an overall second order reaction. All right, now they would like us to calculate K. You got to be careful when you calculate K because the units of K will change depending on the overall order. And it seems like they make a really big deal making sure you get your units right on this one. All right, now pick any experiment that you want and just plug in the numbers from that experiment and solve for K. And so I think I may have used experiment 1. Let me go back and look at the data. Yeah, I used experiment 1. Okay, so here we go. I've got 1.35 times 10 to the negative 7th. That's molars per second. That is my rate. It's equal to K. And from experiment 1, my ammonium concentration was 0.1 raised to the first power. You don't even have to write a 1. If there's nothing there, it's understood to be a 1. And 0.005 to the first power. Now, solving this for K, remember these square brackets mean molar. So this is going to be, the units are going to be molar times molar is going to be molar squared. All right, so when we solve this for K, the value we get is 2.7 times 10 to the negative 4th. The unit, we've got molars per second divided by molar squared. And so it's going to be an inverse molar and an inverse time. So just do the algebra with your units. There is our value of K. Now, it looks like we did a whole lot of math there, but it was really quite easy, just plugging and chugging in numbers. But you could also sometimes, I call it the eyeball method, just kind of look at things and figure out the order without going to all that trouble. Although all that calculation and writing those rate laws down is a great way to justify your answer when they ask you to do that on a test. So notice, first order, you keep the concentrations of all of your reactants constant except the one that you're interested in. If the rate does exactly what you do to the concentration, then it's first order with respect to that reactant. So we doubled the concentration, keeping everything else the same, and the order of that reactant was first order. Had we made that concentration 10 times higher, if it would have been first order, the rate would have gone 10 times as fast. So something that is first order is where whatever you do to its concentration, the rate will mimic whatever you've done, but you have to be keeping everything else constant. All right, second order is just like squaring whatever you do to the concentration. So we didn't have an example of this in that problem, but second order would be, well, if you doubled the concentration of the reactant that you're interested in, you kept everything else the same, the rate would have quadrupled because you doubled the concentration. This is what you do to the concentration. You square it, and then that's how much faster the rate would go. What if you had made your concentration, and it's a second order concentration, 10 times greater, and that reactant is second order? The rate would have gone 100 times faster. So that's second order. Now, zero order is an interesting situation. You change the concentration of the reactant, and nothing happens to the rate. There's no effect. And so we say that it is zero order. And we're going to find out in later things, it just means that that reactant wasn't part of what we call a rate determining step. And so it's a zero order. So whatever you do to that concentration, it has no effect on the rate of the reaction. All right, so let's just go ahead and kind of try and eyeball this one. All right, here's our equation, and again, rate law only involves your reactants, so rate is equal to K, the bromate concentration to some order, the bromide concentration to some order, and your proton concentration to some order. There we go. So now we have 3 reaction orders to figure out. These products, they're not part of our rate law. All right, now let's look. Experiments 2 to 1 keep everything the same, but we've doubled the bromate concentration. All right, so everything else remains constant, double the bromate, and what happens to the rate? It doubles. So we doubled its concentration, kept everything else the same, the rate doubled. It mimicked what we did. This reaction is first order with respect to bromate. Now, justifying your reaction, you can go through and do all that rate 2 over rate 1 is equal to K and then plug in your numbers, that's a great way to justify, or you can use words. You can say, hey, keeping the bromide and the proton concentration constant, doubling the bromate concentration, double the rate, therefore it's first order. You can use words, you can use numbers, doesn't matter. All right, now we have to get bromide's rate order. So what experiments are we going to choose where we only change the bromide's concentration and keep everything else constant? It looks like we're going to be using experiments 3 and 2. So notice we have doubled bromide's concentration, keeping everything else the same. The rate doubles, so bromide is also first order. Now we're left with the proton concentration. Let's see, between experiments 3 and 4, we keep everything else constant. We double it, and, oh, nope, that's not the right experiments. Let's have a look again. 1 and 4. Okay, in 1 and 4, we're keeping the bromate concentration constant, the bromide concentration constant. We double the proton concentration, and the rate quadruples. So that is second order. There we go. Notice what happened. I started looking at experiments 3 and 4, but that wasn't a good choice because we were, yes, doubling the concentration of the protons, but we were also changing other things at the same time. So we really needed to be looking at experiments 1 and 4, where we double the proton concentration, keeping the other concentrations the same. Our rate quadrupled, and so the proton concentration is second order. This reaction order overall would be fourth order. If we went ahead and calculated the value of K, which I'm not going to do, but pick any experiment, plug those values in, solve for K, the K units would be molars to the -3rd inverse seconds. Make sure you get your units right. All right, so I hope that that helps. The problem that we just did, we looked at experimental data and we determined the rate law for the reaction. We know how to get an overall order, and we know how to calculate a K, being careful of our units. All right, I hope that helps. Let me know if you have any questions.